So now we're ready to talk about alkenes, alkynes, and aromatics. I've already introduced you to these terms the last time we talked about this stuff. Alkenes and alkynes still fall under the group that we call aliphatics. Alkenes contain double bonds and alkynes contain triple bonds. Okay? So I'll introduce you to some of them. We'll talk about some isomers of them. And then we'll practice drawing and naming them just like we did. So a little bit of information about alkenes. They contain at least one carbon-carbon double bond. They can have more than one. We would have a diene then. And literally that's the way it would go in the name. We'll see some examples of that. We say that they're unsaturated. The alkanes, the term we use to describe those, are saturated. It means that it is right full of hydrogens. It cannot have any more. But as soon as you introduce a double bond, you have to actually remove two hydrogens from adjacent carbons so that they can make the double bond. It means that they're not full of hydrogens anymore. We say it's unsaturated, right? So again, we had the discussion about fats, right? Saturated fats and unsaturated fats. An unsaturated fat simply means that it's got double bonds in that carbon chain on that molecule. The name, instead of it ending in anes, like ethane, it ends in ene, right? Okay. Again, a similar type little table. We're going to go over some of the example ones. So again, you don't need to draw all the lines. Just put number of carbons. Actually, yeah, we will put the structural formula and then the condensed structural formula. So number of carbons, structural formula, condensed structural formula, chemical formula, name. We're doing the same type thing as we did with the alkanes except with the enes. All right, number of carbons. Well, you can't have a double bond if you only have one carbon. So there is no such thing as methene because you have to have two carbons to have the double bond between. So we actually start with two atoms, two carbon atoms. Structural formula, C, double bond C, H, 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 H. And condensed structural formula, CH2, double bond CH2. So we squeeze it together there, okay? Its overall chemical formula, C2H4. And what are we calling this thing? How many carbons? So what do we call it? F, right? F. And it has a double bond, so we have to put an ene on the end. F-ene. It's ethene. Okay? This historically has been also called a vinyl molecule. And I'll talk more about that a little later on. But that's an old name for it. Ethene is the new name. But I'll talk a little bit more about that later. 3. C, C, and it doesn't matter, I'll put the double bond there. H, H, this has H3, and then it's got another H off to the side there. Notice these are all sp2, right? The guys that are flanking the double bond are sp2. They're triangular planar shape. This guy here is an sp3 hanging on the end. CH3, CH, double bond, CH2. C2H, how many of them are on that one? Oops, C3H6. What's the general formula for alkenes? How many H's are there compared to the C's? 2 times. So C N H2N. There's no plus 2 because we had to take the 2 away in order to make the double bond. That's how you could actually check to see if it's saturated or unsaturated. Let's say I give you a formula that has a whole bunch of C's and H's, and you do the quick math and you find that it's N plus 2, 2N plus 2 for the H's, then you could say, hey, that's saturated. That's an alkane. But if you end up with just C and then N, and then 2N. Oh, you can say, hey, that's unsaturated by 1 unit of unsaturation. You could stick 2 more H's on there, okay? You'd also find that to be the case for the cyclic ones. To make a ring, you actually have to take 2 H's off to close the ring up at the end, right, to do that type of thing. So you'd find that that's the truth for cyclic alkanes as well. What's this going to be called? Prop what? Propene. All right. Next, 4. Now we run into trouble with 4. I'm actually going to draw 2 structures in here. Actually, no, I'll only draw 1, and I'll put the second one on the second page. The first one, let's put it as C, and I'm going to put the double bond right away. So H, double bond, and then C. And then that's going to have a CH2 and a CH3. And this H is going to go up here. Actually, I've drawn the condensed one. The other H, oh no, that's, what have I done? That's H2, isn't it? I don't have enough bonds here. Okay, fixing. That, you know what I'm tripping over here, because I want, and now I've got a different color. Because on my next situation, I have these isomers that Emily really didn't want to talk about, and I thought about it all last night. I was getting all excited so I could disappoint Emily by talking about these special type of isomers. Okay, so that's not a bad picture right here. C, 2 H's, double bond, H, and then CH2, CH3. Okay? And in terms of the condensed structural formula, CH2, double bond, CH, and then we keep going down the chain, CH2 and CH3. Okay? And C4H8. And now we've got to introduce a special naming system, because I put the double bond right here after the first carbon, but there's no reason why I can't put the double bond over here after the second carbon. Okay, so the position of the double bond becomes important. This double bond comes after the number 1 carbon, so we call this 1-butene. I now am putting a number right before the parent name to indicate the position of the double bond. Okay? Yep. Oh my goodness gracious, that's an exciting question. Like, so how does that position of the double bond affect the characteristic of the molecule itself? It will subtly, but exactly how? I can't answer that. I was terrible at organic chemistry. Except move the double bond over. That's exactly correct. Yep. And what do you think we're going to call it when we move it over? 2-butene. But there's 2 forms of 2-butene, which I don't usually introduce, but yeah. So let's talk about the 2-butene. Let's put the double bonds in here. So again, this is 4 right here. Another one for 4. So the structural formula, I've got it in the middle now, which means I've got a CH3 out here, and then I've got an H this way. And now I've got a decision to make, because remember I've taught you that you can't rotate a double bond, because that pi bond, right, remember it's got the attachments above and below, and if you rotate it, you break the bond. So double bonds don't rotate very well, which means I can either position the next CH3 up here or down here, and they actually make a difference. Let's put it up here, CH3, and then the H, okay? Now, when you do a condensed structural formula, it's going to look exactly the same. This is going to be CH3, CH, double bond, CH, and then CH3. And if I do the other version, again, this is 4, C, double bond C. This time I'm going to put the CH3 up top, and I'm going to put the other CH3 down below, CH3. H, H. Condensed structural formula is going to look the same. CH3, CH, double bond CH, CH3. And these are all C4H8, C4H8. And you're right, these are both 2 butenes, but one of them has the CH3s together, and one of them has the CH3s on opposite sides. When we wouldn't call these things structural isomers, because they have the same connections and they've got the same chemical formula. That's what our definition of structural isomers were. These two are actually what we call geometric isomers. They've got the same connections and the same formula, but due to the restricted movement of the double bond, they actually have slightly different geometries, even though their connections are the same. We call them geometric isomers. The way we name geometric isomers has to do with the position. So right here, this thing shuts off every time. So right here in this one, we've got opposites. Computer's catching up with me. It's a little slow. We've got opposites. We call this the trans isomer. This is the trans. Trans means opposite, right? You take the Trans-Canada Highway, you want to go to the opposite side of Canada. Trans means opposite. We call this guy, when they're together, cis. I have no idea where that comes from. So this is actually called cis-2-butene. And this is called trans-2-butene. All right. We've encountered our naming systems. I could do a 5. There would be some cis and trans guys. I'm not expecting you to know a lot about this cis and trans thing. I just wanted to introduce it to you. If I asked you a question on the test about cis and trans, it would be directly about the butene. I wouldn't, mix it up and try to be too mean on you. Okay? All right. So let's not worry too much about 5 and 6 and 7. You're getting the idea, I think. So the general formula is N, CN, and H2N. And that's for alkenes that have 1 double bond. If it's got 2 double bonds, then another 2 would have been taken away. Then it'll become 2N minus 2. Then you've got 2 units of unsaturation. 1 to get you down to the 2N, and then another one gets you minus 2. Now in my next series of slides, I go over how to name them with branches and all that type of stuff. And I've turned this into a handout as well, so we don't have to draw all the pictures. But on this handout as well, I've also got the rules of naming alkynes, triple bonds, and the rules are very similar. So I'm going to introduce you to alkynes first, and then we'll talk about alkynes, and then we'll do all of the naming in one shot to finish off the class. Let's now first write down about alkynes. They're also unsaturated. We would say it has 2 units of unsaturation. So now I've got things like ethyne and propyne. Again, when I get to butyne, I would have to have numbers to position the triple bond. So again, I'd have a 1-butyne and a 2-butyne. General formula, because we have to remove another 2 hydrogens, CnH2n minus 2. That's if it's got 1 triple bond. There are no geometric isomers for triple bonds. They're sp2 hybridized, which means they're linear, right? They're all in a line. All those molecules are straight linear. So there is no flipping situation. There's only geometric isomers for double bonds. And I think we're getting to the point where we're going to practice naming. So I'm now going to switch back to this PowerPoint right here, naming branch-chained alkenes and alkynes. It's actually easier to name alkenes and alkynes. The parent chain must contain the double or triple bond. So it's now not the longest chain necessarily, but it's the longest chain that contains the double bond or triple bond. Because remember, we called that special group of atoms the functional group, and the functional group must always be in the parent name. It's what defines what the molecule is. When numbering, begin with the end that's closest to the double bond or triple bond. So now our numbering becomes even easier because the double bond always kind of trumps the branches. Because again, it's the functional group, and the functional group gets the main, gets the main characteristic of that molecule. So we give it the smallest number. So easy. Main chain has a double bond or triple bond, and it gets the smallest number, and then we in a ring structure, number will always start at the double bond. So if you've got a ring with a double bond in it, that defines number 1, with number 2 being the next guy. We'll do some examples. And then if we have multiple double bonds, we can have dienes and trienes, all right? And we'll do some examples. Name the branches as before, put everything together, and away you go, all right? So let's zoom in here. I know I made these pretty small. My next handouts, I don't have them quite as small, but I think you can see them okay, can't you? Can we see them okay? All right, so let's slide this thing over here. Let's name this guy right here. So I've got a chain here, and again, you might think 1, 2, 3, 4. You're right, it is 4. But right away, that double bond indicates the smallest number. So there's my 1, there's my 2, and there's my 3. So because we've got 4, I always name that last one. Anything that's beyond 4 needs numbers, right? We saw that when we did 4. We had a 1 butene and a 2 butene. So anything that's beyond 4 needs numbers. If it's 3, then you don't need it. It's just propene because there's only one spot it can really go. So this is a 1 butene. Now we need to name our branch. It's a methyl. It's in the number 3 position. It's a 3-methyl-1-butene. All right? Here we don't have any branches. Nothing to worry about for branches, but we've got 2 double bonds. Again, we need to number because we need to position those 2 double bonds. This is a 1, 2, 3, 4, 5, 6. All right? Now, it's a hexene, but it has a double bond after the first carbon and a double bond after the third carbon. So this is a 1, 3 dash hexa, and we put the A on the end of the hex, right? Just like where we said but, well, I just said but it's actually buta, and it's actually tetra, penta, hexa. If it's ending with something like ene, we don't put butaene because the E and the A don't work together very well. So this is hexa. We put in a di, and then we put the ene. So in this one, we've got the 2 numbers, and we've got the di to represent 2 double bonds. Hexadiene. Okay? Let me know if you want me to stop anything, because I'm going to clear this screen here. Clear the screen? Clearing the screen. And Smart Ink is off. Oh, that's because I'm still running this thing. Get out of the way. You get out of the way. Smart not connected. Clear Ink. Still works. Yep. Yeah, I'm going to move this guy over. Okay. All right. Numbering from this end, right? 1, 2, 3, 4. Oh, look at there. There's a C3H7. You might think the longest chain is 1, 2, 3, right? And then I've got 3 more, 4, 5, 6. But I've got to have all the double bonds in my chain. So you might have thought 1, 2, 3, 4, 5, 6 is the longest chain, and it is, but I've got to have all the double bonds in my chain. So even though I only go to 5, I don't choose that because all double bonds have to be in the chain. what kind of a branch is this? Propyl. So base name, 1, 3. And what am I writing as that last part? Pentadiene. Pentadiene. So we've got the main chain. Where is my propyl group on the number 3? It is a 3 propyl, and I dropped my dash in there. 3 propyl. I've got a cyclic structure. My 1 is going to be either here or here. And I always then count 2 on the other side of it. But what's going to give this the lowest number? That's the question. 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 6. So I go 1, 2, 3, 4, 5. You start at the double bond and go across it to get to 2. Don't head the other way. So this is, and you don't need the number in this case to say that it's a 1 cyclo, actually how many are in this chain? So you don't need 1 cyclooctene because it defines the 1 position. You just need cyclooctene. Cyclo, and you do put 2 O's, it's funny. Octene. So cyclooctene, it looks like cyclooctene, that's funny. But that's how you write it, cyclooctene. And this is a 5-methyl. 5-methyl. Oops, no dash in there because it's a continuous word. There's no things in there. So 5-methyl cyclooctene, and I did a really bad job of trying to get that to come together, but if you have a space in there too, I'm not concerned about that. Okay? All right, that's a fun one. Let's clear the ink. Let's move along to the next one. Oh, so here we're drawing some enes. Again, drawing enes are easy. Drawing anything is easy. 1,3-pentadiene. So, oops. I got to change my pen here. Did I miss one? Did I miss one? Oh, we did that as an example?
No, that was the first time we did it.
We did it when we did an example?
So, like, that was the first time we made. There was no point.
So it's the same thing? Oh. Oh, there you go. I didn't even realize that. Okay, then let's skip it. I was just cutting and pasting. Didn't realize it was the same molecule. Good eyes. So B. Pentadiene. Again, same thing. I just draw 1, 2, 3, 4, 5. 1, 3. Put in my double, oh, that's a horrendous double bond. Put in my double bond after the 1 and after the 3. Now after the, on the 2, I put a methyl, CH3. And then I load up my H's just as before. This guy has 2 bonds, so I need an H2 there, right? This guy has 4 bonds, no H's. This guy has 3 bonds, he needs an H. This guy has 3 bonds, needs an H. And this guy, H3. Okay? For this double bond right here, notice I've got an H and then 2 different things. This would have cis and trans isomers, but I'm not going to make you draw those. But I could have this big branch sticking down and this big branch sticking up. It would have cis and trans isomers. This guy has 2 H's that are identical. There would be no cis and trans isomers across that double bond. I'm not making you worry about that stuff. I'll only make it an easy one if I'm going to get you to do that. Okay? I'm looking to clear. Moving over for one more. Cyclohexene, 1, 2, 3, 4, 5, 6. Just put the double bond somewhere to begin with. That defines my, oops, I didn't mean to write that. That defines my number 1 position right there. Get rid of that dot. That defines my number 1 position. So that's 1, 2, 3, CH3. You could have went the other way around, 1, 2, 3, and put it off of there. Okay? Gonna clear. Scream at me if it's no good. Gonna move down here to some double bonds, triple bonds. Okay. I didn't leave a whole lot of room here. I think I'm gonna write the name on the side here. Looking for the chain 1, 2, 3, 4, 5, or 1, 2, 3, 4, 5, 5. Doesn't make any difference, right? So it's looking like it's a pent, and it's a pentyne. You might think, hey, let's count from this end because it's going to give me the first branch. But remember, the triple bond or the double bond gets the lowest number. That means I have to start from this end. 1, 2, 3, 4 for my branch over there on the 4. So there's 5 in total. So what's my base name on this? What's the end part? It's a pentyne. It's a pentyne. But I do need a number to define where that is. Yeah, it's a 2-pentyne. And now I can have a dash here. And now I need my branch. It's a 4-methyl. You know what? Actually, 4-methyl. That's good. That's a good name. But you know what? We really don't need that 4-methyl because there's nowhere else to put that methyl group. I can't put it there because there's no more H's. I can't put it there. I put it there, it makes the chain longer. I wouldn't mark you wrong. That's the subtle one. But technically, you don't need that 4 because there's only one place that the methyl can go. But I wouldn't be picky on that. But you technically don't need the 4 on that. Clearing. Can I clear? Clearing? Clear. Moving over. Which one's my number 1 carbon? What side? Left? Yep. Because it's got to have the smallest number, right? 1, 2, 3, 4, 5, 6. With a branch up there. So what's my base name? 1, 4. Hexa, because I need to put something before. Diene. What a great word. Hexadiene. That's fun. It's like we're learning a new language. So, and then what goes in front of this? A 3-ethyl, right? It's an ethyl? 3-ethyl. And if we looked at, we might be restricted on that as well. And we are. Look at, there's no other places to put that, but I'm not going to get picky on that. 3-ethyl. Looking to clear. We okay, clear? Clear. And now I think I've got 1 or 2 to draw. Just 2 to draw, maybe? 2 to draw. And then I got to go back to my PowerPoint for your homework. And yeah, we'll stop there. Again, drawing is easy. Draw your C's, put your double, triple bonds, put your branches, fill with H's. So penta, 1, 2, 3, 4, 5. It's a 2-ine, so there's my triple bond. And I'm not very good at this on the computer, but it's okay. And I need a 4,4-dimethyl. 1, 2, 3, 4. CH3. CH3. And then load with H's. This is an H3. That's got 4 bonds. That's got 4 bonds. That's got 4 bonds. H3. Heptadiene. 1, 2, 3, 4, 5, 6, 7. 1, double bond there. 2, 3, 4. So it's after the 4, right? Our double and triple bonds go after the number. A 3-ethyl. 1, 2, 3. C2H5. A 6,6-dimethyl. Right down here. CH3. CH3. And what do we got? An H, right? I need an H on that guy. 1, 2, 3, 4. No H's on the second one. 1, 2, 3. A single H on that guy. No H's. No H's. No H's. H3.